So good morning. Whether I am good morning. Whether I am audible to all? Am I audible? Okay. Good morning. So actually last few days I was trying to show you that sine pit of PWM that I am not able to show you. So first today I will show you that. Then I will go to the today's subject. Okay. This is the code as I was telling you yesterday. So just I have copied this value from Excel, but you can optimize. You need not to take this much long decimal digits. Okay, as per your requirement you can choose it. And I have discussed about the code earlier. Okay, sine PWM, normal PWM, we have learned it. Simple, in the earlier code you see we are just putting a fixed duty cycle, but here the duty cycle will be changing according that value I am taken from the array. This array, it's basically nothing but 0 to 360 degree sine theta, nothing else. Okay, so as I told, to optimize the code to get the sine theta, what you can do, you can write another function, because to get the sine theta, and why I am going to 156 and all, that is in the some next course I will be taking detail about the microcontroller, basics of microcontroller. So there we will tell all the fine tuning and what these are, what are the things, all these things. Okay, so here you see I have reduced 20 counts because this is to this is the date time I have given. For 16-bit and higher bit microcontroller there is a separate register, date time generation register is there, but for 8-bit controller most of the controller don't have that, so you have to use some technique to generate that date time. Okay, so now let us simulate it and see. Okay, one I'll close it. You see here what I have done. One I have taken filter. So what I'll do? Yeah. So this A, it is connected to channel A of the scope is connected to OCR1A. B is connected to OCR1B, but it is after filtering. After filtering, I am using one filter to show you. And C is connected with the channel B. That means this A will give non-inverting, this is inverting. In between B, it will give the filtered output. So let us see that. You see now that yellow color. Let me increase the time base. You see the yellow color waveform, that is the non-inverting waveform, and the pink color waveform, that is the inverting PWM. And this, if I pink color, if I filter it, you will get that blue color. So similarly, if you remember our motor control, there is an inverter. So in that inverter top and bottom leg, if you give this kind of PWM signal, then finally we will get that output. Okay. Anyway, this just I have shown you that what are the things. I tried to give you a glimpse that what are the things required, but if you want to know the things in details, then I'll be teaching you some subsequent courses. Okay, you can write different methods are there to generate PWM. Space vector PWMs are there. Then another using complex variable. There are so many techniques to generate the PWM. Okay, so that we will see later. So just today I have shown you that. Yesterday also I have said this is the thing. So similarly you can generate for all the phases, how many required and all that we'll see later. Okay, now today we will be discussing about encoder, because you know while we will be operating with BLDC machine, you need to know the rotor position. Correct, you need to know the rotor position. So normally people use Hall effect sensor, but nowadays this encoder is a good choice for a very precise and critical application. People will use the encoder. So we will be using synchronous serial interface. So we will learn it. What is that? Basically, we will understand what is that. So let me take one. So this synchronous serial interface is a widely used interface standard for industrial application, especially for rotary encoder. Okay, you know, in case of parallel communication, the number of, say I want to transmit 13-bit data. I need 13 wire, 13 connections for parallel communication. And moreover, if any particular one bit is not transmitting properly or there is some error, the measurement having a huge error. But if it is a serial communication, then it will be going as a packet. All those possibility will be reduced. Okay. The main thing, this is the simple block diagram. So this is your master device. It's a master-slave communication. So master device will be your PLC or microcontroller, and slave will be your encoder. That will be connected with the shaft of the BLDC or induction motor, whatever may be. So microcontroller will give some clock pulse to encoder, and the output register of the encoder will transfer the data to microcontroller or PLC. Okay. So the data is shifted out when the sensor, that means the encoder, receives a pulse train from the controller. We will be knowing slowly how it is. When the last significant bit LSB is transmitted, so once the LSB is transmitted, it needs a pause or hold for a certain period. Once this time is elapsed, then again you give the clock to the sensor, then again it will transfer the data. Okay. So normally this clock and the data are transmitted as per RS-422 standard. This is a military standard for because here the main thing is it's a differential data. Differential data means that is not single-ended. Means what is happening here? There is no ground. If there is no ground, then say the error, some noise or something, it will be equally added with the signal. Both the positive and the negative signal. Then when you are converting from this differential data to single-ended data, what will happen? You are subtracting. Okay, let us understand what I am trying to tell. Say this is your positive data, and say negative side data is like this. So while you are converting this differential data to single-ended, because there is no ground, your ground is not there. So when you are converting these things to single-ended data, basically you are subtracting this. So now say one, so this is, say this is empty, and say this is minus empty. Now one error is there, means noise. It is adding with the both channel, because error will be added with both channel. So basically here it will be a controller or something, whatever that device is capturing, it will be receiving empty plus ET, that error. Another channel also it will be receiving the same thing, empty plus ET. Now when you are converting to single-ended data, you will be minusing this from this. So you see this ET will be cancelled. So error, naturally, if you use differential transmitter, the transmission noises will be cancelled in a better way. Okay. So here I am going to show you the encoder specially, which I have with, that is maybe 25-bit. I have in my lab on encoder, so that data only I have taken. You see, this is the timing diagram. As I was telling, so initially when I am not getting the, when I don't want the data, my clock will be high, you remember, because that things, it will be reflected in the code. Okay, so once the clock, while I don't want any data, the clock should be, or idle time, you can tell, the clock should be high. When I need the data, position data, you first make low the clock and then high. So when you are giving the first clock, means giving the clock, and during the first raising edge, the output register of the encoder will transmit the MSB, and every raising edge, it will transferring the corresponding bit of the position data. And once once this my thing is 25, as I told, I am taking 25 bit, so it will go up to 25, clock will go 25 plus 1, 26. Then my entire LSB transmission complete. So for the encoder, whatever I have used, that minimum clock frequency is 50 kilohertz and maximum clock frequency is, I think, 100 megahertz or something. I can't remember exactly. So it is something range like this. So clock should be in between. So you can select your clock frequency based on your PLC or microcontroller clock, or the speed of measurement you need. So it is to be optimized. You should not keep it very high unnecessarily, clock. So once the entire position data is transferred, the LSB is transferred, as I was telling, you have to give a pause. So as per this protocol, that SSI protocol, your minimum pausing time should be 21 microsecond, and maximum you can keep it anytime based on your speed of operation you need. Okay, and once pause time means you have to make the clock high, and once this pause time is elapsed, and again you can send the clock to the sensor, and you will receive the data. Okay, so this I have taken from that my CRO. So as I was telling, this is 2, 3, 4, 5, 6. As I was telling, this is 24. This is 24, 25 bit. Okay. So now you see, once this is my clock. So once it is falling, my data is not transferring anything, but the first raising edge, it's given the data. So this is my 0, 0, 0. This is also my 0, 0, 0. So this is my 0, 0, 0, 0. This is my 0, 0, 0, 0. And this is this 1, 0, 0, 1. This is 0, 1, 1, 0. This is 111, and this is 1010. So you see, if you are giving pulse, clock you are giving, it is coming immediately. Okay. It will give the position data. This will be in degree. Then you convert this value in decimal, you will get the degree. This is the test hardware. As I was telling, it is a differential data, and the controller I have used, that I have done long back. It is Atmega 88 IC, small IC I have used. That is long back I have tested this. So that time single-ended means so much microcontroller was not there. So, and as I was telling, the data and the clock, those are differential. There is no ground. So I have to convert that the differential signal to single-ended signal. So for that I have used one IC. It is MAX 1486. MAX 1486. This is the IC. So this is a connection. You can see the data sheet of this. You will be getting this. Then I am connecting. This is the data as an input, and clock. It will be giving. It will give to microcontroller. That is that output. Okay. This is the test connection. Now I am coming to the code. Okay. So you recall the timing diagram. So here I am using one user defined function called read position, and in that I am using another function. It is shift in. So the arguments are data pin, clock pin, and the number of bit. In this case it is say 25 bit. And as I was telling, there is a, if you see the timing diagram, there is a high for it is 21. So there there should be some pause time. So I have taken arbitrarily, that is 32 microsecond, and after that it will return the sample, and again it will start the count. So let us see what is that shift in function. The shift in function also taking the argument of data pin, clock pin, and bit count. It is very simple. I am initializing the data as 0. Now I am rotating one for loop which will go 0 to bit, 0 to number of bits, that many times. And I have used this things means it is shifting. I am shifting. It is left shift. Say 1. This means it is 0 1. No shift. Say 1. I am shifting 1 bit. That means this 1 will be shifted here. I will get 1 0. Say if I do like this, means it will shift 2 digit. It will be like this. From here it is shifted 2 times. Okay. So what I am telling, say how I am storing the data. I am just whatever coming, it is shifting and doing OR. Shifting and doing OR operation. You see, I am reading that, then shifting and OR operation. This is equal to OR. Bitwise OR. Okay. So you see, code is very, very simple. So every bit you shift 1 bit, then send the clock. So here you see I am using clock frequency is 6 microsecond. So my frequency is 1/6 into 10 to the power 6. That much. So 1/6 means 1.67 0.67 megahertz. I have used that clock frequency. Every clock it is collecting the data, then it is shifting 1 bit, doing the OR, and continuously it is doing. So finally you will be getting the entire position data, and that things you are returning. Okay, you are returning that you can use main function. So this read position you can use in the main function. Okay. So this is all about the code to, so you can, if you connect this encoder with the shaft non-driving end of the machine, very easily you can find out the rotor position, rotor angle. Some few videos are there in my channel, so you can type this keyword, there will be some playlist will be coming, so that the same explanation will be there, and 2 more video will be there for code explanation and how to connect with PLC. That things will be there. And this book also available, a detailed book is available in Amazon. You can type my name, so many books will come. In that book, this book will be there. So if you want to read in details, you can take this book. So now the thing, yesterday I have given a glimpse. I have given a glimpse about the connection. Okay. So now we will be knowing. I will be telling you this connection slightly in details. Say you can take a contact. So you see, I will be using 2-wire thing, 2-wire connection. So I will be using these 2 contacts. Say this contact name I am giving forward, and this contact I am giving reverse. Now you see, operator by mistake should not press both the thing. If he press also, then it should not operate. I have to make that simple protection. So for that, I am using one push button. This is my push button, and this is one relay. Here 24 volt is connected, my relay coil supply. Say I am giving, this is the name as PB1, and this is the coil name is I am giving 1. Another push button I am using, that push button name is 2, and this is my PB2. Okay. So now what I am doing, I am using another relay. I am using another relay contact, which is this F. I am giving that F. And here this relay having both normally closed and normally open contacts. Okay. So this 24 volt I am taking here through one NC contact of 2 and one NO contact of 1, and this F NO normally open contact I have wired, I will wire here. So now see here what will happen. If I press this PB1, then the relay coil 1 will be energized, and the normally open contact of 1, it will become closed, and through this F will be energized, and once F will energize, then this contact will be closed, and the drive will be started to operate in forward direction. Now somebody, if by mistake he press this PB2, what will happen? That time this coil number 2 will energize, and that normally closed contact I have put in series with this connection, so this will break, and immediately this F relay will be dropped, so the system will stop. Similarly, for the reverse operation, Here I will use the one close contact of 1 and open contact of 2, and this is my coil reverse. Okay, so same thing. If anybody press, suppose I am operating PV2, I press this, then this contact will become normally closed, and 24 volt will be coming through this, and it will energize the relay coil R, and this thing will be closed, and the machine will be, motor will be started to rotate reverse. By that time, if anybody press the PV1, this will become open, then this relay will drop, system will stop. So this is called the, this is the protection normally used. It's a very simple relay based protection. Okay, sometimes this is while you are operating the machine, you have to keep on press, but suppose I want to single one press, it will start to hold it. Okay, you recall this connection, recall that previous connection. I will be drawing it. Say this is the, so here it is, this is the 24 volt. So I am using some coil, and this is the ground, this is your forward. Okay, so this is my coil 1, means this is push button 1 is for my forward operation. This will be normally closed. Okay, so this is coming from 2 for the protection, and the another NO contact of 1, another NO contact of 1, I will be wired like this. This is coming from the, sorry, it is coming from the F, and I am connecting like this. Now you see what will happen. Once I press PV1, then this contact 1, it will be closed, and 24 volt it will come through this, and the relay F will energize, and once the F will energize, then this parallel which I kept it, this is also become closed, this NO will become NC. Now once I release this push button, even though this become again normally open, but through this is still that relay will energize. This is called latching, and it will keep on, once you press and release also, it will start to go forward. Now if by anybody by mistake, if anybody press this 2, then this NC will become NO, and this relay will drop, it will stop. So similarly for reverse, here it will be 2, this for protection, which is from 1, then this is going to the relay coil name R. Here you give a NO parallel with R. Okay, this is 24 volt. It is very clear. If you want that by push button should be pressed or once pressed operation with protection, how to do, you have understand? Very simple. Now in the potentiometer, there is 3 terminal. Normally it is 1, 2 and 3. So these things connected to this terminal, connected to 1, this terminal connected to 2, and the variable connection connected to AI1. So my potentiometer connection is over to change the speed. Now coming to the brake. So as I told, say this is your motor, this is your motor, and this is connected with your driven equipment. So this is your motor, this is the load, and in between, say there is a gearbox. There is a gearbox. Forget about the drawing, I am not able to draw properly. So normally what will happen here, two pulley will be there. And there will be some brake shoe. Here. There will be some brake shoe, and this brake shoe will be preloaded by spring. So this is called, one thing it will be connected with thruster brake, and this is connected with electromagnetic brake for protection. So one supply is coming here, and here this brake will release and machine will start to operate. If you remember, I told that I can configure this to contact as it will be closed when the machine is developed full torque. So I am using two power contractor. This is power contractor 1 and this is power contractor 2, each having the coil supply. Both the things having the coil supply. Okay. So what I will do, I will use another relay which having two normally open contact, and the 24 volt, this here I will connect 24 volt, and this terminal I will be connected with this relay coil and it will be grounded. And these two NO contacts, say it is 2-1 and 2-2, name. So this coil supply, it will be connected through, say this is the plus of this one, it will be connected through 2-1, and this is another one, this will be connected to 2-2, and this is the input 3-phase, this is the input 3-phase or 2-phase because it is a EM brake, DC, whatever may be, and this is connected to your thruster brake, and this is connected to your electromagnetic brake. Now you see what will happen. Once the machine is once the motor is developed the full torque, then this R1A and R1C, it will be closed. Then the 24 volt, it will be energized this coil. If the coil is energized, then the normally open contact of 2-1 and 2-2, this will also become closed. If become closed, the coil supply of the power contactor, it will be getting through this, and for this it will be getting through this, and this both the contactor will be closed, and the electrical supply will be extended to thruster brake and electromagnetic brake. And once the supply is extended, then it will oppose the spring preloading, and this brake shoe will release, and the motor will start to drive the load. So this is the typical connection used for commercial VFDs in the market. So this is the thing. 1 minute. So this is all about today's class. Now some 2-3 minutes are there. Is there any question you can ask? Is there any question or I'll move? Okay. Then thank you so much. We'll meet tomorrow.